Yeah. So I'm Arnaud Delorme from here at INC, and this is our project EEG-DaSh, first year CRCNS. And this is a project here at UCSD. We work with Amit Majumdar at the San Diego Supercomputer, and this is a project in collaboration with Oren. I was going to say a few words at the end about this part of the project. This is an infrastructure project. So it's one of the few infrastructure projects. Even though we're both computational neuroscientists, I train on spiky neural networks and Oren does a lot of modeling. But this project is mostly centered on infrastructure. And it's centered on BIDS. So most of you probably already know BIDS. That's the main way to share data these days. Brain imaging data structure. So I was one of the participants that created the EEG part, so the part on electroencephalography. And basically, our project is about making this data, which is in a data archive, available to the machine learning and deep learning community. And so what is BIDS? BIDS is a way to organize your data. And so here, there's an example of folder with files. So basically you have folders and files and you name your file in a specific way. And they are not named right, then the BIDS validator throws an error. And so BIDS is not a database. It's not a new format. These are just files and text files. And it's not a data sharing tool. So once you formatted your data into BIDS, then you upload it to different database. And to format your data, it's actually very complex. So we have a tool that we developed to share your data. This is called EEG-BIDS. And basically you give it some files and it's going to export your data. And then you can upload it to a different platform. This is part of the EEG Lab ecosystem. So EEG Lab, we're well known for EEG Lab. That's the main used software for processing EEG data. What we created in Terry's lab more than 25 years ago. And that's still leading 25 years after. So that's part of this ecosystem. And here, so this is an illustration of what our project aimed to do. It aimed to take some BIDS data and then aim for the machine learning community on top. And basically what we need to convert to is the BIDS data into a PyTorch data set. So that's what our library is doing. So we ingest data from OpenNeuro which is the largest database for EEG. So that's a collaboration with Stanford we have. So we are NEMR and OpenNeuro is at Stanford. So we are the EEG face of OpenNeuro. But we're also ingesting BIDS data from OSF, Zenodo, Figshare. So we have ingestion pipeline for all of these. And in terms of compute, we have Amit on the team. And so we have a direct link with the Neuroscience Gateway, which is another NSF-funded project for the compute part of the project, for the computing data quality metrics. This is just a slide about the infrastructure, where basically what we do is we try not to store the raw data. We're just a layer on top of the raw data. So we are running this database, this MongoDB server, and then the data can be different location. For example, for OpenNeuro, the data is on S3 buckets. So we just refactor the data into these PyTorch data sets that people can use for machine learning. And we also allow for some search, parsing of the data, preprocessing. So I'll just show that in a second. So this is our website. And you can see here all the data we have ingested so far. So it's 254 experiments from 13,000 people. And then you can see how the data is organized. I'll show you what kind of data we're sharing. This is from which part of the country this is, and also which part of the world. Also here you see that sharing is growing. This is sharing of EEG on OpenNeuro, NEMR, MEG, and intracranial EEG, and you see that's growing. There's about 460 data set right now. When we started, it was 30. When we started 5 years ago. This is the type of multimodal data, because we're very interested in multimodal data. So the EEG is often associated with behavior, MEG often associated with fMRI. So all the multimodal data is compatible with bits and stored with bits, along with spikes, for example. This is the type of age distribution we have in our data. Lots of undergrad students, you see the big peak at 20, so it's not uniform across the population. Here, this plot is in terms of number of channels. Most of the EEG we distribute is 64 channels with a little bit of 128, and most of the MEG is above 250 channels. So that depends on the amplifier that recorded the data. The experiments, here there's different types of experiments. Visual, you see the majority are visual experiments. And what's also interesting is that we have very little clinical data. So there's lots of reasons for that. Clinical data cannot be easily shared, whether it's in Europe or in the US, but that's a real bottleneck to this kind of approach, is the amount of clinical data. There's less than 10% of clinical data. But we have many different types of clinical data, but every time it's just like, a few dozen subjects. We also have developed in our lab this framework that's called HED, hierarchical event descriptor, and that's a way to describe your event across experiments. So for example, you do experiments in France, Germany, and the US, you might have different event names. So that's the way to uniformize everything. And we also have a HED bot, basically, that's trying to tag your data, trying to tag the event in your data and put them in buckets. Okay, this is a stimulus, this is a response, etc. So you can do metadata analysis. When you pull data from our database, you can know that's a response for sure. You don't have to look for in every single experiment about what type of event it contains. And basically, this is how you call the library. So just Python script. You call here, you want the data for this task, resting state. And then you run your model. The library was downloaded. We just released it really 2 months ago. It was downloaded 67,000 times. And I'll explain you why in a second. The main reason is that we created this competition. And so we got it accepted at NeurIPS. And so that's a competition for EEG Foundation Channel. We did that because we thought, well, how do we popularize our library? Well, let's create a competition. And we got lucky because it was retweeted by Jan LeCun, the director of research on AI at Meta, who has more than 1,000 followers. So we got a lot of interest into our competition. This is everyone involved, a lot of people from UCSD, including Scott McKeag and Terry, and the core team. So we run the competition on the top in collaboration with a group in France that runs a tool called CodaBench. And we had 2 challenges. Challenge number 1 was to predict reaction time from the EEG. So fairly easy task. Challenge number 2 was to predict psychopathology. And we gave a database of about 3,000 people. And we had a test set that was hidden of about 300 individuals. And so basically people submitted their model and we run their model ourselves on our server and got the results. And this is how the ranking was done. Some of the computation for this competition was done on Expanse, where we have direct access to some GPU time. So Expanse is right on the other side of the whole, about 100 yards from here is Expanse. I invite you to go see it. It's pretty impressive. It's one of the biggest supercomputer in the US. Amit is right here if you're interested in seeing that. And also, we're also contributing to a tool that's called Brain Decode. And so that's an infrastructure where once you formatted your data set to PyTorch, you have a model zoo. Basically, you can run about 20 different models. So it's easy to pre-process your data, etc. So we're also part of that ecosystem. This is the challenge results, which ended last week. And the winner is this team. We're happy that they're actually a neuroscience lab. The 5 next ones are not neuroscience, they're pure AI people. But
you heard it here first, folks.
And so here is the winner is very interesting because he ran a mask autoencoder. So here you see on the left these type of models. You just mask some image and they try to reconstruct the image. So he did the same with EEG. And the advantage of that is that you can run very large model. You don't have to label the data. And the take-home message, basically, he won because he used massive amount of data and massive amount of compute. So that's basically the story, back from 2010, that, okay, you need lots of data. And just wanted to, in his own word, why they think it's important.
This raises the critical questions for the field. With so much energy and computation poured into yet another EEG foundation model, what is the collective return? Instead of a model race, I believe we should build a shared, standardized ecosystem using common datasets, unified evaluation metrics, and transparent baselines that will truly advance EEG decoding in the future. I also believe what I just mentioned is precisely the direction that this 2025 EEG Foundational Model Challenge promotes.
Okay, so now I'm going to let...
this raises a critical...
I'm going to let Oren say a few words about the features. This was about the raw data. So people process the raw data, but there's also features.
Yeah, so the major goal of this project is indeed to support deep learning applications on EEG, MEG, and it typically applies directly to the raw data. But we believe that there's also importance for working directly with features. Okay. So if you take the data and transform it into features, it reduces the dimensionality, which allows for more compact representations. So it's helpful for generalizing. Not always you have large amounts of data to train models with deep learning models with billions of parameters. And it also allows for interpretability using features that have meaningful names like the power at the alpha band or measures of connectivity, etc. And essentially it bridges neuroscience and machine learning, because now we can apply classical machine learning. So not always you have to go directly to complex deep learning models. You can use support vector machines, random forest, etc. So we also wanted to include tools for features, and it turns out this takes time. So you have to come up with some design principles and. So by the way, I said in the previous slide that this feature toolbox was developed by Dr. Aviv Dotan, who's here in the audience. So the design principles put a lot of emphasis on issues of performance. So we use the PyTorch framework, so it allows for interfacing with deep learning, but also parallel processing, for example, across subjects, if you have files with different subjects, batch processing across time windows. And the feature extraction was designed for improved performance. There's a feature extraction tree, and this tree logic is enforced by the package. So for example, if you process data from a single channel, you can extract signal variance, Lempel-Ziv complexity, and then if you extract power spectrum, you have things like root total power bands. Once you have the power spectrum, you can calculate the spectral moment, spectral entropy. The thing is that once you calculated something, you don't need to repeat it again. But in other feature toolboxes, you typically do the calculation every time again when you call a feature. So it wastes a lot of time. And here it's more efficient. And also it's designed for flexibility, modular implementation. And I will not go into these concepts of decorators. So Aviv already implemented more than 35 features, and we're working on adding more features. For example, measures of critical brain dynamics, which is a major thing in my lab we love, but we want to add more, and we are open to other suggestions, so you're also welcome to contribute. That's it. I think we're ready for questions. Maybe we have some thank you slide. Arnaud, do you have more?
No.
Okay, question? Yeah, you're good.